not doing, try your best, guys, yeah, to find any application that suitable for you, yeah, during this time frame. Okay. Okay. Then that midterm exam grade, I also need to find time to finishing touch. Yeah, when DA finish to mark, yeah, grading your assignment, and soon we will announce. But of course, it takes time for that. Yeah, so be patient for that grade of your midterm, and then also the average grade, yeah, for first quiz and midterm. Okay, and then for last week we have a graph, yeah, and then inshallah today for spanning trees and greedy algorithm. So K10 and K11. Let's go for the last week. Yeah, recap a bit about graph. Then we represent our graph with adjacency list and adjacency metric. And then we have three algorithm or three method: BFS, breadth first search; DFS, depth first search; and topological sort. And then we know already that BFS and DFS similar. It equal V plus E, and topological sort because, well, actually this as you can see, this is use DFS, yeah. So they're also similar, yeah, V plus E, topological sort, and then DFS, all similar, yeah, V plus E, yeah, big theta V plus E, DFS, and for BFS, DFS, this, yeah, equal V plus E. So they are, the three of them are similar, yeah. And then we also discuss about how to prove that the correctness point select topological sort by that color, gray, white, and black, yeah, for topological sort. But understandable. And then what is that forward edge and cross edge and so on. Yeah? Most important is that back, yeah, back edge. It's the most important. That cycle, it means, oh, well, actually this is the one can distinguish if it is back edge, it means cycle. And then they couldn't be. Yeah, this is a tree and back edge is important. Okay. Then because that B, it is that back edge is the one that make DAG, directed acyclic graph, existed, yeah, without any cycle. By the one that we really care, why we said it is important, because yeah, with this back edge, then there is a cycle. Yeah. It means there is no DAG. Yeah. There are no back edges. Okay, so that's the recap for our graph. I wish before 5, guys, yeah, we will finish, so don't worry. My family also got ill. I myself ill and then recover, and then again my daughter also got ill, my wife. Actually, this um, the circumstances is not that good. I mean, fasting is okay, but the changes of weather, yeah, that make our body getting weaker. Yeah. Then we prone to ill. Yeah. I got cough, snorting, and yeah, then back. Yeah, I mean, hope to member of family, and then I recover, and then jump to my kid, and then back to me, and then so I'm, yeah, I'm not so fit. Also, shortening the lecture of framework based programming, yeah, from after Duhur, and then because really it's very difficult when you are not fit, yeah, 100%. Okay. Okay, so we want to finish up topological shot because it's really interesting, yeah, that what we discussed last week. Yeah. So again, we revisited DAG, directed cyclic graph, that it is directed graph. Yeah, it means there is a arc. There is a arc here, like arc. Yeah, so arc, directed graph. I mean there is a arc, but no cycles. Yeah, no cycle. So easy, just check that B, yeah, that back edge. It is often used to indicate precedences among event. For instance, event A must happen before B. We already discussed about this. And for example, is parallel code execution, especially in distributed computing. All of our multiprocessor should have this. Because remember, I think it's never happened now, yeah, that your computing power devices, it doesn't matter, gadget or your laptop or your desktop, only have one core. Yeah? I think maybe at least have 4 or 8 cores now, yeah? And that's why they need this paradigm, yeah, that the DAG can be applied to get so-called parallel code execution, that each core will execute their own as long as the process not overlapping. Yeah, then this DAG can be used, to get the optimal one. Which one is the most optimal one? Which one is the most uh, path? Uh, the series of path and can give us the better solution. Yeah? Using a total order can be done using topological sorting. Yeah, we can do already. And then we already discussed about uh, how to prove, yeah, yeah, that for gray, white, and black. Yeah. And the most important is the this, yeah, gray. The back edge is the most important one. Yeah, when you cut this, it mean cycle. It mean contradiction. It mean it shouldn't be there. Yeah, the other okay. So this is contradiction. I mean, if you cut this, yeah, by contradiction. This white okay, yeah, white okay, black should be okay. Black it mean already finished. White it mean the newest one. Yeah, I mean become descendant. Yeah, now we will continue for spanning tree. So what is spanning tree? Spanning tree of G for that, the symbol of our graph, yeah, G. Graph G is subgraph, which is a tree. So there are trees, subspanning trees, there are three. Then contain all vertices of G. With the subgraph, it means it contains all vertices of G. For example, you have G like this, the left side. Then spanning tree of G can be seen here. So it might be you got decreasing edges here, but the vertices should be there, all. It's A, and B, let's say until, let's say T, yeah. So all there, yeah. So A, B, yeah. Let's say until T. Only some edges disappear. Maybe also can be the same, yeah, exactly the same, our graph, but it might be uh, decreasing, yeah. So some edges disappear. And then what we really care is about how to find this spanning tree in minimum edges, because the vertices the same, right? The number of vertices in our spanning trees are the same. Okay, so the problem is how to find the minimum one. Min depend of how many edges, yeah. Then yeah. That's why this because minimum spanning tree MST. It's quite common topic. It's very common topic and can be used for many problems actually. This it is undirected, so there is no arc, and then connected graph G equal to set of vertices and edges. Connected graph. And check here, guys. Yeah, the spanning tree. This all connected. Yeah, all vertices connected by edges. None of none of vertices alone. Yeah, none connected. So each vertices always have edges among them, right? So nobody been alienated. Everybody, when every vertices is connected. Yeah? Every vertex is connected. Then we also introduce so-called weight function W, weight function, where W map all of vertices into some number. Yeah, this is some number. So assigning cost or length or other values to edges. For instance, this 6 can be 6 kilometer or 6 kilogram, yeah, or 12 liter or whatever. Yeah, so any value. So they assign some value to edges connected to vertices. Spanning tree. So a tree that connects all the vertices. Connect all the vertices. All the vertices. How about above? It is spanning tree? You might say, no, Pak, because for instance, yeah, I don't need this. Yeah, okay, correct, yeah. Let's say I don't need this 7. Yeah, correct. Because 9 to 15 can go through this, yeah, for instance, 5, and then 14, 3, 10, and this. Also, maybe not 7. Let 7 still there, yeah. But you delete, let's say 14, so can be. So this you delete this. It doesn't matter as long as for each vertices we can pass through, yeah. We can pass through via edges. It doesn't matter. Okay, yeah. This, or maybe not 8. It is quite small, but I want to delete this 12. So okay. Delete this, and then you delete 6. Okay. We will have this algorithm how to find this minimum one. So the definition of MST, minimum spanning tree, then this tree that connects all the vertices. The first definition, yeah, that connect all the vertices, and then not just connect all vertices, but you have to minimize this WT, the weight of that T. Let's say this is the subtree T, sigma, this weight of U to V, yeah, W U V, where U V the element or the subset of T. Okay. Okay. Then we discuss about optimal substructure. Yes, MSTT, make my minimum spanning tree T. Then we divide this MSTT become two sub trees, yeah, T1 and T2. T1 and T2. So you can check, yeah, all connected. Okay. And okay, so we partition this MSTT become T1 and T2. Okay. And then removing the HUV partition T into T1 and T2. WT become this WT plus WT1 plus WT2. So let's say this, yeah, you can check this, guys, the one that connected T1 and T2. Okay. So this, let's say the WUV. You can check, right? So WT total, yeah, the weight of T equal to WUV, this connector, yeah, plus WT1. WT1 is this. Yeah. WT1 means this. All of the weight in T1 and WT2, this. All of the weight in T2. Then we claim that T1 is the MST of G1. G1 is the minimum spanning tree of G1. The set of V1, E1, yeah, subset, the set of all of the vertices in V1 and all of the edges in E1. The subgraph of G, induced by vertices in T1, induced by vertices in T1. Also, G2 is the MST of G2. Similarly with this, because you replace the number 1 with number 2. Yeah. So G2 equal to V2 comma induced by variable. Greedy choice back to the greedy approach. Yeah, we have DP, dynamic programming, and greedy choice or greedy approach. We always remember that it is inspired by DP actually, dynamic programming, that greedy. But in many cases, DP is too heavy, and then many greedy approaches already successful. Not all, yeah, but it is already okay. We already discuss what is the criteria to be able for applying greedy, yeah, greedy approach or greedy choice. Right? I remember recalling 3 and 4, yeah, the step 3 and 4, that when it is only one left, yeah, choice, or the other one, if you are safe to use greedy approach, and then also okay, yeah, back to that lecture last week, not last week, last 2 week, yeah. Okay, again, we will emphasize that greedy choice property. Locally optimal greedy choice yields a globally optimal solution. Actually, I give the example of that hill climbing. Yeah. That actually they are, if more than one, local optima, then actually what we aim is to get this global optima. Just local, just local. L local, then this G global optimal. Just local. Theorem. Let G equal to VE and let S subset of V. Subset of V, yeah, that means vertices. Okay. And then let UV be minimum weight H, mean weight H in G, connecting S to V minus S. Because it's subset of V, mean less than V then, yeah, the number. So we have UV, and back here, yeah, UV. Let's say this is UV. Let UV be minimum weight H in G connecting S to V minus S. Then UV element T minus some MST of G. MST of G. Okay, we prove, yeah, we prove. So number 1 first, yeah, that if you have S, right, this S, and then this is V minus S. Remember this set is all V, yeah, all V. G equal to, yeah, VE, yeah. That is correct, yeah, S and then V minus S. Okay. Okay, proof, yeah. Suppose UV not subset of T. It is not subset of T, yeah, not element of T. Not element of T. So then look at path from U to V in T. Look at path from U to V in T. Okay. So it was this, yeah. So this is in the beginning. This UV is the, how to say this, the minimum one. So this UV. So originally this is UV. This UV, yeah, UV. This is UV. Yeah, yeah. UV. UV. Wait, yeah, wait. But suppose that UV not element T or not subset of T. So this is why this red color. Suppose not. Suppose not. Then we need to look at path from U to V in T. Okay. And then we need to swap XY. XY. What is the XY here? It is the first edge on path from U to V in T that crosses from S to V minus S. S to V minus S. So this is not, and that means we need to find the first edge, and then we choose this, yeah, XY. Choose XY, yeah. The first edge on path from U to V in T that cross from S to V minus S. Remember that T is the one, this the one that this partition T, remember, yeah. T1 and T2. And because we said UV is not, and then we choose XY, it means XY is shortest one. Yeah? Shorter than UV. When we imply that suppose UV is not element T, then we choose choose XY, the next one, the first edge on path from U to V in T. It means what? It means XY, XY this, yeah. It means shorter than UV, right? UV, okay. Shorter. This improves T. Yeah. But when improve T, okay, so this is not minus yet. It's like then UV element, it means, oh, this is some MST of G. This is not minus. This is like then UV element T. This the element T. This is correct element T. To revise my statement before. This is not minus, but it's to emphasize that UV is subset of T. Okay. Let's check, yeah. That it means what? XY less than UV. Mean improve that T. Yeah. Improve that T. That T mean it is already minimum, yeah. Then you suppose that UV, UV the one who connected, yeah, UV this. You suppose or assume, usually by contradiction like this, yeah, we assume it is not. Then you move to another one, yeah. Let's say in this case, no, we don't have, but let's say it is have, yeah. Let's say this. But because we say that WT this, yeah, should be WUV and then become WXY, yeah, because we swap to XY plus WT1 plus WT2, yeah, this, okay. So it means it is minus 23, then you improve. Let's say this MST, let's say the total weight, yeah, let's say 100, yeah. And because we move to XY, let's say it become 98. Let's say this assumption. So it means improve, right? From 100 to 98 now. Yeah. This, yeah, improve T, shorter. But this become contradiction because they already mentioned and stated that T is supposed to be MST. They already minimum one, minimum spanning tree. It is impossible, yeah, to find any configuration who shorter, who has less weight than T. Yeah, it's contradiction. Okay. That's usually in DAA, we prove by contradiction. But of course, it's not that easy to prove and then write down, yeah, our idea clearly that reader can follow up our idea, yeah, in crystal clear, the beginning until the end. It's not easy, but that's the only way. Yeah, usually much easier to prove by contradiction than straightforward solution or straightforward proven. Yeah, straightforward proving. Okay, and then we want to present the algorithm for MST, and then we start by generic MST algorithm, yeah, generic or general one, yeah, generic MST. So general MST, the parameter G, our graph with W, small w, and then we assign MT to A, yeah, contains edges that belong to MST, that A is our usually array, yeah, array A. Then while A does not form, a spanning tree do. I mean, not yet, okay. One vertices, one vertex, of course not. Then, okay, second vertex, it means you have two vertices now, yeah, for the A. Till you got that spanning tree. But while not form this spanning tree, then do this. Find an edge UV that is safe yeah, for A, safe for A. Then you combine, yeah. So UV, the set of UV union. So the A union set of UV, then your sign become the new A. So you A that A, the existing A, add up with UV, then become the new A now. And you assign to A, then return A. What is safe edge? This is safe what? This is the edge that does not destroy, not destroy its properties, not destroy the its properties. Imagine this, this that if UV you said always make this T MST, so it's impossible to have another configuration to get T to get T become how to say MST. It means improve that T. You got, as I said, yeah. So you assume T is MST, already have the weight totally 100, yeah. And then assume UV no, there is XY, and then become 98. This is impossible. That is impossible. This already MST. MST. So this is the shortest one to make this all happen, yeah, the configuration. And that's why the safe edge, it means the one that not destroying this. So configuration will keep MST. So of course, 100 is gradually. Yeah, let's say you build that T gradually, but before get 100, let's say, oh no, I'm 50 now, and then you add up some additional H. Let's say become okay. I get 3 now, yeah, become 53. So this building of MST, and so far you got 53. You add up these 3. You call it, this is safe edge to add up in our MST so far. Yeah, edge that does not destroy its property. Remember that UV, it is the shortest path. Yeah, like how to say, the lightest weight or shortest path, like the MST. Okay, and then more specific MST. It's not just generic. The same parameter G and W, small w. Then again, you set A empty first, then edges that belong to MST. Then while A does not form a spanning tree, do again. This is only find an edge UV that is safe for A. And then now we specify, become 3.1 and 3.2. Okay. For 3.1, this make a cut S, comma V minus S of G that respect a cut, a portion, yeah. And then take the mean weight H, minimum weight H of UV, connecting S to V minus S. So that's it, yeah. Make a cut S, comma V minus S of G that respect A. Then take the minimum weight H UVs connecting S to V minus S. Then again, yeah, A union UV, you assign to the new A. And we have algorithm for that. Yeah. Okay. We acquainted with prim Jarnik algorithm. It is vertex based algorithm. Vertex based. So based on the vertex. Gross 1 3T, one vertex at a time, until all vertices cover. Yeah, until all vertices will be covered. The prim Jarnik algorithm. A cloud covering the portion of the already computed. A cloud covering the portion of the already computed. Then label the vertices V outside the cloud with key V, the minimum weight of an edge connecting V to a vertex in the cloud, and key of V equal to infinite, yeah, if no such edge exists. Okay, so we will label of the vertex V outside the cloud with key V. Yeah. So this is the algorithm of prim Jarnik pseudocode. You have G, W, and R. This is here, so graph and then weight and then R. And then you have V, VG. You assign to Q. Q is this vertices out of T. Vertices out of T. So all of the vertices of G, and then you send Q. Of course, Q a lot. Yeah. And then for each U element Q, then you assign infinite to key U. And then for QR, you assign 0 first. And as usual for this is what? This is like predecessor, yeah, like pi, predecessor of R. Like pi, predecessor, pi. Pi R nil. Of course, in the beginning you don't have any predecessor. It is U, starting from U. Okay. And then while Q it was all vertices, yeah. While Q not equal 0 until Q0, then yeah, do. You extract min Q, making U part of T. Extract min Q, send to variable U. And then for each V element adjacent, make the next of U, yeah, adjacent U, do. If V subset or element Q and WV is less than key V, then okay, now U is the predecessor of pi V, right? Right. So remember that's UV as well, like this U, then V. So I mean you become predecessor, yeah, of V, right? This is predecessor, predecessor. And as usual, to make it easier, they use that Latin symbol, yeah, pi. And then UV also become key V. This is we call it updating keys. That's the example, yeah, you see from vertex, yeah, from vertex, guys. Yeah. Okay, so let's say assume, yeah, from A, vertex A. Okay, and then what is adjacent vertex A? Of course, B and H, yeah, BH, because we look for the one who got shorter length or lighter weight, yeah. So it means for an 8 need to be compared, of course, yeah, for less than 8, right? When we choose A, and then of course it's black, yeah, black, and it means already done, yeah, we already take into account A. Okay, we choose 4, yeah, because 4 less than 8, so it means the A we choose B. Okay, and then this is blackened, yeah, because B also blackened. Yeah. Okay, again then from B, yeah, B and A, actually B and A. So you have 11 from B, yeah, 11 and 8. Of course, 8 will be chosen, yeah. So 11 need to cross out. Okay. This also A also actually have 8. Yeah. So it's the same. Which one? And then let's say arbitrarily, yeah, you choose B to C. I mean the edge one. So you choose this. Okay, no problem. Prim charning. Then C then become blackened. This. So far 4 and 8. And then again, yeah, all of this need to choose, yeah. Okay, I have 11. Oh, this cross out, yeah. Okay, and then I have 8. I have 7. Yeah, from all of this from ABC. I have 4. Yeah, so 8, 7, 4, and then 2. Okay, you already know, yeah. Oh, of course, 2 is the the least one, yeah. So 2, then 4, and then 7, yeah, and then 8. Of course, we choose 2, yeah. Then okay, so we choose I. So 4, 8, and 2 blacken. Then again, from this you need to find which one. Yeah, you have 8, you have 11, you have 7, you have 4, yeah, you have 6, you have 7 also. Which one? As you already your instinct, yeah, yes, it is 4. 4 been chosen of 7, 6, 7, 11, and 8. Yeah. And then we choose then F, yeah, blacken. Okay, and then you again, yeah, which one, yeah, of A, B, C, I, and F, which one that you can add up, yeah, that UV in order to make it a sub tree. I mean that spanning tree, yeah, but to make it minimum 1. all of them, yeah. So 8, 11, 8 no, yeah. 7, 6, 7 again, 14, 10, 2. Well, of course 2, yeah. Okay, and then 2 chosen, yeah. Been chosen. To G then, yeah. G. Okay. Then again, what to see? Of course, cannot go to 6, yeah, because become circle, yeah, circle. We don't want to find. We actually can, but it is not preferable because you will already have the path, yeah, and then you can save instead of 6, you can do 1, yeah. As you can see, yes, it is 1 is become the this one, yeah, comparing to others. Okay, so we go to H now. With the 1 is the last UV, yeah, the edges UV, add up to the our set, yeah. Okay, and then you don't want to go to 8 because this useless, yeah, you already can go from H to A by that the element of others, yeah, 2, maybe can go from here, yeah, here, yeah. So you don't need this 8. So then only this, yeah, 9 and 10, yeah, left. Oh, actually to 14, yeah, but 14 we don't need because we have already CD and CF, yeah. So we have 9 and 10 then, yeah, to go to E. Yeah, then as you can, your intuition said yes, should be the 9, this one, correct. Yeah, this. Okay, show this, yeah. So A, B, C, I, and then G, F, D, E, H, yeah, can be seen that we don't need this 8, for instance, yeah. We don't need this 7, 6, and so on. So this configuration, yeah, the configuration is the minimum one of our spanning tree. Yeah, this, okay. This configuration is the minimum one that we are able to visiting all of the vertices, yeah, by any path. Yeah, of course, it's up to you the path. As long as there is as long as there are paths and you can visit each of vertices, then we call it MST. Then correct. Okay, MST. This prime joining algorithm. Yeah. Then again, that Q. That actually we already have that PQ. Yeah, remember PQ? Yeah, long time ago. Yeah, but still remember, yeah, that PQ to help us for data structure. A PQ is a data structure for maintaining set S of elements, each with an associated value called key. Okay. We need PQ to support the following operation. First, we need to build PQS, initialize PQ to contain elements of S. And then extract min, returns and remove the element of S with the smallest key. Okay. Yeah, you can imagine this, yeah. Oh, yeah. Actually, we need that special data structure to all the time when we grab to add up that edge, add up that edges into our set, but to make sure when that adding up will maintain our MST. And then modify key S, comma X and new key changes the key of X in S. That means you're changing the new key, replacing this X. We also already learned that binary heap, that binary heap can be used to implement our PQ, priority queue. And then it's easy to see that binary heap, yeah, you know, binary tree, binary whatever, yeah, it is big O(n). We can return back to our courses, yeah, back to that time, yeah. With PQ is big O(n). And then for extract min and modify key, big O log n. And of course, thanks to that binary heap, yeah, only big O log n. Then we want to evaluate frames chronic, I mean frames to make it shorten frames running time for time. So this absolute B, how many vertices you have? Yeah. T extract min plus big OE T modify key. Yeah. Then the time become big O V log V plus E log V. And you can check this, yeah, by asymptotic analysis. V log V plus E log V. Then Pico E log V. Because edges, you can check this, yeah. If you have three, yeah, three vertices, edges only two. So how many it is, yeah? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 9 vertices. And how many edges? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So 8. Yeah, you can check this. Yeah. So V log V plus E log V. Then we can why it is only equal E log V. It means we can discard, yeah, V log V. We can discard V log V. Because it's in asymptotic analysis, it is insignificant. Yeah. E log V is more significant. Then when you find that if it is by Q, yeah, that Q, and by what do I say? If we have a option, yeah, to implement by some data structure, you can see that for Q you have array, binary heap, and Fibonacci heap. For T extract mean, yeah, and T decrease key, and the total can be seen in this table. Yeah. So if by array of course extract mean, yeah, if you extract mean, pick OV. How many vertices you have? Of course you need to visit to find the minimum, and then you extract and find the minimum. For decrease key, it is constant, yeah, pick O1. Total, it means V times V, yeah, so V square for array. Binary heap, extract mean is log V, pick O log V. Decrease key, pick O log V also. Total, pick O E log V. This back to this time. Okay. For Fibonacci heap, extract mean is the same like binary heap, pick O log V. For decrease key, it is constant, pick O1, amortize. The Fibonacci heap, and the one that Fibonacci, remember that Fibonacci, but not use that approach for our heap. And then total is this, yeah, pick O, P log P plus E. So this is okay, which one? Because depend on the situation, maybe pick O, E log P is already okay, or you want to improve P log P plus E. So that for text based, yeah. And then that's also good, guys, in our life, that if somebody already invented or found something, in order to be a successful person after that guy, yeah, we can't just simply following. Also in the market, yeah, market leader, for instance, in the market, you have market leader, that if you are following exactly like what he or she did, head to head, it is, how to say, it's like suicide, yeah. This Kruskal, yeah, after she Prim Charnik, based on vertex, and then Kruskal also have another day. Okay, how about my baseline is from edges. I Prim Charnik and vertex, then me should be edge, yeah. Yes, then it can be, yeah. So edge base, not vertex. Kruskal is edge base. Yeah. Prim Charnik, TJ, yeah, from vertex. Yeah. But the idea is similar with Brimjanic, yeah, that you add the edges one at a time, and in increasing weight order. Increasing weight order. Okay. Then the algorithm maintains our variable, yeah, can be kind of array, but of course it's not totally array, yeah, it's kind of a variable. Yeah. A forest of trees. Forest of trees. An edge is accepted if it accepted. An edge is accepted if connects vertices of distinct trees. It should be this F8, yeah. This should be swapped. Only to forget, yeah. Edge is accepted if it connects vertices of distinct trees. Okay. We need a data structure that maintains a partition, i.e. collection of disjoint set. Yeah, disjoint set. So we have mixed set S and then variable X. So that S and then union X, you add up X, then the addition you send to the new S. Then union Si, comma Sj. So S minus Si Sj union Si union Sj. Then become the new S. Find set S, X. You return unique Si element or subset S where X element Si. Find set, I mean you find the element X in your S. Okay. The algorithms at the cheapest edge, the cheapest or the lowest value or the lowest edge, the cheapest edge that connects two trees of the forest. So this is the pseudocode of Pascal, yeah. G and then the parameter W, small w. As usual, empty set, empty send to A, and then for each vertex V, element VG, do each vertex V. Because remember we based on edge, yeah, but of course we need to another edge add up. It means you look for what kind of adjacent vertex, yeah, close to you. Right. Then we make set V, and then sort the edges of E by non-decreasing weight W's. As usual, yeah. DA always say the fancy word non-decreasing. It means increasing. Increasing. They say non-decreasing means increasing. Okay. Increasing weight W. Okay. For each UV element of subset E, in order by non-decreasing weight 2, in order by again increasing, my goodness, increasing. Okay. For each UV element E, in order by increasing weight 2 this. If find set U not the same, like find set always like this, U and then we go to V, UV. If find set U not the same like find set B, then A union UV will assign to the new A. Then union UV, get written A. Okay, example as usual. Yeah. Okay, you have similar with that case study of that rim churning, right? But because we look for from the edges first, yeah, it means what? We need to look for, we need to find the least or the shortest length or the lightest weight of all of the edges in that graph. Of course, one, yeah, it is the shortest one or the lightest one. Okay, then okay, make it this. I choose. I mean, blacken. Yeah. Okay, great. After that, the rest. Yeah, the rest. Because you see that this is yeah, make set V, and then for each blah 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 blah, sort the edges this, and then you find. Yeah, accept yourself. Yeah. Then of course you got two. Yeah. It's also blacken this. Yeah, two. And again after that, yeah. Okay, you choose only one and two. Which one? Well, actually, can be also this, yeah, guys. Two and two. But in that case, arbitrarily we choose this. Because it can be also you choose this. But in this case, no, I choose that C to I, yeah, or I to C. But then after that, anyway, because it's arbitrary, again, then actually you also choose, yeah, that because both of them should be chosen, yeah, should be chosen. Okay. And then you got 1, 2, and 2. And which one after that? Of course, 4. Yeah. This. But actually also can be here, yeah. But arbitrarily you choose that A to B or B to A, yeah, this. Okay. Okay. Don't worry, it will be, yeah, because anyway, you will be. And then, okay, and continue 6, yeah, 6, and then 7. Actually, after this, yeah, which one? Yeah, actually the 7, yeah, 7. I mean, another 7, because again, it is arbitrary which one. It's up to you, but anyway, it will be chosen. Okay. Then after that, 8, correct, yeah. and then another 8, this, and then 9, yeah, okay, yeah. But you can also check here, yeah, actually, when it is 8, it is chosen, but see, yeah, it is 8, no, because why? You already, B and C already connected, right? So actually, see, even though actually it will be chosen, yeah, this, but no, we cancel it, yeah, we cancel it. Okay. Again, after that, 9 already done, yeah, 9. Okay. So this is already done, yeah. And then 10, yeah, actually want to choose 10, but remember, DE and anything from F, yeah, GF or CF already got, yeah. So we will cancel it, this, yeah. We want to choose 10, yeah, but see, we cancel it, right? We cancel it, no. Yeah. And then again, because we until finish, yeah, and then we choose after that 11. But it's already connected, yeah. A, B, H already connected. We cancel it, right? We cancel it. Okay, so cancel it. Next, which one? Haven't choose 14, yeah. 14. Remember D, E, and F already get connected, yeah. Okay, and then yeah, we choose, we cancel it, and yeah. Okay. So that is a crucial, yeah. Okay, disjoint set as list. Disjoint set as list. Each set, each set is a list of elements identified by the first element. First element. And then all elements in the list point to the first element. Okay, this disjoint set as a list. For union, add a smaller list to the larger one. Then for find set, is equal 1. Yeah. Because our spatial structure make it constant, yeah, to find. Union UV is equal which one? Minimum of CU, comma CV. And here, yes. So that disjoint set, so F1. And then 2. So you have to connect this here, 2. And this connected to this. Okay. If 3, okay, you got this, and then this connected to 1. If 4, connected this, and then this connected to 1 itself, this, yeah, 1 itself connected to himself. And if I have A, B, C, by A, okay, I connected out myself, B, and then connected again in here, C, connected C, and then connected in here. And then you add up, yeah, from 1 to 3, 1, 2, 3, 4 with A, B, C, then you will cut this. Yeah. Okay, go there, and then so on. This for the disjoint set as a list, yeah, because we also talk about so-called disjoint. Here is our disjoint. This, yeah, collection of disjoint set is this. Yeah, this. Okay. Then about running time, yeah, initialization, big O V time. Yeah, because so many vertices to get how many edges, yeah. I mean, we need to find. That's why we need big O V time. And then sorting the edges, big theta E log V equal to big theta E log V. Why? Remember always, yeah, that if you have 3 vertices, actually there's just only 2 is enough, right? Not 3. Of course, this also can, but for what is, yeah? If it is, let's say it is 2 and 3 and it is 4, yeah. So 3 vertices and you only have 2 edges. Okay. So log V it is okay. I mean, it can be the same. It can be the same edges, yeah. But for sure, edges in MST cannot. For instance, 3 vertices, yeah, and then you said, oh, there is 4 edges. Oh, it's of course impossible. Yeah. Maximum, if you have 3 vertices, you will have maximum 3 edges, yeah. But in this case, I still no, yeah, because you don't need it, right? But of course, it is like my simple explanation. Yeah, you have to please read the book and answer the question why big theta E log E equal to big theta E log V. Remember this, V replacing E. May I give you like very simple Very simple, stupid reasoning, but please find out why. Yeah. Okay. Big OE call to find set. Of course, we need to find all of the edges so far to find set. For union cost, this let TV equal the number of times V is moved to a new cluster. Remember the union, yeah, or I say A plus union something, yeah, and then you assign this, yeah, and so on. The number of times V is moved to a new cluster. Each time a vertex is moved to a new cluster, the size of the cluster containing the vertex at least doubles. PV less than log V. At least doubles, yeah, at least doubles. Okay. So total time spent doing union, sigma TV, V element V, yeah, less than V log V. V log V. So total time is big O E log V. E log V. Then you can check. This is crucial, yeah. How about Prem-Charnik? It's like very amazing. You can check, yeah. Prem-Charnik. Equal, yeah. Let's say that binary heap, yeah. Big O E log V. This the second one. E log V, yeah. Okay. So amazing that somebody else idea inspired somebody else, somebody ideas inspired somebody else ideas, totally different thing, but they say the same thing, different perspective, and then they got equally optimal solution. So this is also very good in our life, that we can be a somebody, we can be a successful person, we can be somebody that found a solution. Yeah. For me, many things in DA really get me inspired, guys. I'm like, wow, it's amazing, yeah, that actually it can be done. Yeah, I mean, amazing, yeah, really amazing. That wow, yeah, yeah, the same thing, yeah. That grab is the same, yeah. The grab G the same. Only Prim Charnik, see the vertices, yeah, vertices. Kruskal, oh, I don't want it because somebody already uh, obtain it, yeah. You should also like also the same like my life, yeah. I want to success like that. I want to follow, but remember, it cannot just copy paste, because that particular successful way from that particular person only can be achieved by that thing. Yeah, we cannot just simply follow copy paste all the time. Yeah, all the thing like that Pak Kruskal. Yeah, and then okay, I just based on age. It been actually similar with that. I mean, prim charting. Yeah, but not totally V. Let's say V prime, V prime. Like how to say, like alter of V. Yeah, and then actually this V prime is E at the edges, but the result the same. Yeah, because E log V. Yeah. Once again, guys, for the detail, please read by yourself. Yeah, I did my part many years ago. Many days I spent to read, to prove so many algorithm. Then I don't want it anymore. Yeah, I mean too much. Of course, I also like this, but it is your partner, yeah, to enjoy the beauty of algorithm. Yeah, how to prove like this by contradiction and some mathematics and blah blah blah. It's very beautiful. It is your part, not my partner. Yeah, to get this big E log V. It's very interesting that the same thing. Yeah, I mean life is the same. Yeah, I mean this life and your life is the same. Yeah, we live in the same planet Earth, the same atmosphere. How could somebody? Oh, it's different. Your life is different. The same. Only and also the thing is we need to give different perspective maybe, yeah, in order to get success. Like any successful person, yeah, like Prim Charning with vertices and Kruskal with edges, and they are exactly got like equally, yeah, success, yeah, to find the total time is because Ilokvi, yeah. So it really inspired me, like wow, it's amazing. It's only story and some symbol that really inspired me. Okay, that's it, guys. Yeah, I said, like maximum 5 o'clock. Yeah, but inshallah less than, yeah, because also it's, I just recover and then again got coughing and snorting, and then my kids and my wife also is very annoying. Yeah, but it's okay to burn our sin. Yeah, this Ramadan, holy Ramadan. Uh, it's better to have something a bit difficult now, yeah, then in hereafter, yeah, in dunya, I just okay, I obey, I accepted. Ya Allah, oh good Lord, it's okay, yeah. Just be patient, okay? Okay, that's all, guys, yeah. Oh yeah, the next week is the second, as I said, yeah, second quiz. Inshallah tonight I will release, yeah, the document. Yeah. Then you guys can have more time, yeah. It's not only 1 week, but 2 weeks. That's why I changed my approach. It was really only 1 week, but no, it's kasihan. I mean, you are very pity for you guys. We have so many courses, so many assignments, so many responsibilities in life. Yeah, if I give you another a week, yeah, so in 2 weeks, I think it is my contribution to give you a lighter, yeah, can alleviate your burden a bit. But of course, you still need to do. But time now is a bit, yeah, spend a bit, yeah. Okay. Okay, great. That's all. That about that spending minimum spending 3, ya MST. Okay. I will stop now. Yeah, and then I wish you all the best, guys. Yeah, and you can start your project. Yeah, about building or create any program or game, whatever. Use that BFS, BFS, or DAG or topological and whatever. Yeah, you can check the previous question. Yeah, it's similar with this, of course, like different date, yeah, and then different deadline. Yeah, okay. Okay, that's all, guys. Also have a good time. Please, nice to find your PPT, ya, para become a PPT para pencari takjil, ya. Please don't focus on that fried snacks, ya. Please adapt more, ya, your fruits and also vegetable, because I know many of you like that fried thing, ya, sempol, cimol, cireng, or that nampol, yeah, was that pentol cora and so on, yeah. But please adapt more fruit and vegetable. Yeah. I know it is not crunchy, yeah, and spicy or and delicious like snacks thing, yes. But this it's not good if you are add too much snacks, fried snacks. Yeah. Okay, please find a way that make yourself healthier. Yeah. Okay, thank you guys. Have a nice time. Yeah. Assalamualaikum and good afternoon, guys. See you later.
Waalaikumsalam. Thank you, sir.
Thank you, Mas.
Thank you. See you guys. Have a nice time.
Thank you,
Have a nice
sir.
time. What a wonderful day. Okay. See you guys. Thank you.